Right now, deep inside a dying star somewhere in our galaxy, something almost impossible is happening. The center of that star is no longer a star. It is a black hole, and yet the star itself is still there. Its outer layers stretching for millions of kilometers, still glowing, still whole, still completely unaware that its own heart has just collapsed into a singularity from which not even light can escape. From the outside, nothing looks wrong, but inside, an event horizon has appeared, and what happens next depends on things you would never guess. Rotation, magnetism, angular momentum. In some cases, the star explodes with unimaginable violence. In others, it simply vanishes from the sky without a sound. Tonight, we uncover the strangest kind of stellar death known in the universe. Before we go any further, if this kind of deep space exploration is something you enjoy, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. To understand how a black hole can appear inside a star that still looks perfectly whole from the outside, we have to start with the star itself, long before anything strange begins to happen. And we have to start with the kind of star that can even attempt this, because our sun cannot do it. Most stars cannot do it. What we are about to describe requires a specific kind of stellar giant, and even among giants, it requires one that lives at the outer edge of what physics permits. The stars we are talking about are the true monsters of the galaxy. They begin their lives with somewhere between 20 and 100 times the mass of our sun. Some are even larger. They form the same way any star does, from a cold cloud of hydrogen and helium gas that begins to collapse under its own gravity. But because they carry so much more material, they behave in a fundamentally different way. The heat inside them is more intense, the pressures at their cores are more extreme, and the fuel they burn does not last nearly as long as ours. Our sun is expected to live for about 10 billion years. A star with 20 times the sun's mass will burn through its entire life in only about 10 million years. A star with 60 solar masses might last only 3 or 4 million years. 100 solar masses, maybe even less than that. These giants are cosmic short-lived flames. They ignite. They shine with a blue-white intensity that outshines millions of ordinary stars combined. They pump out enough ultraviolet radiation to ionize the gas clouds around them for hundreds of light years. And then, in an astonishingly brief window by cosmic standards, they die. The reason they die so fast is simple. To hold themselves up against their own crushing gravity, they must produce enormous amounts of energy in their cores. That energy comes from nuclear fusion, the process by which lighter atomic nuclei are forced together to form heavier ones, releasing a burst of energy each time it happens. In our sun, this fusion runs at a stately pace. Hydrogen becomes helium slowly, quietly, over billions of years. In a massive star, the same reaction proceeds hundreds of thousands of times faster. The star is not being frugal with its fuel. It is burning it as fast as it possibly can, because if it did not, gravity would win. For most of a massive star's life, it does exactly what our sun does. Deep in its core, hydrogen nuclei are fused into helium. The energy release streams outward, pushing back against gravity, holding the star up. This is a balance so precise, so perfectly tuned, that a star can maintain it for millions of years without wavering. But the fuel is finite. Eventually the hydrogen in the core runs out. For our sun, this will one day be the beginning of the end. It will swell into a red giant, shed its outer layers, and leave behind a small, dense ember called a white dwarf. Nothing dramatic, nothing explosive, just a slow, quiet fade over billions of years. But for a massive star, the loss of core hydrogen is not the end. It is only the first of many endings. When the hydrogen at the very center is exhausted, the core contracts under gravity. That contraction squeezes the core harder, driving its temperature higher. And at high enough temperatures, a new kind of fusion becomes possible. Helium nuclei, which the star has been quietly accumulating for millions of years, can now be fused together. 3 helium nuclei can be forced into a single nucleus of carbon. Carbon can be fused with helium to make oxygen. The star has found a new fuel source. It burns brightly again, but helium burns much faster than hydrogen does. Where the hydrogen phase might have lasted 10 million years, the helium phase in a massive star might last only a few 100,000. And when the helium in the core is gone, the same thing happens again. The core contracts, the temperature climbs, a new fuel becomes accessible. This time, it is the carbon left over from the last round of burning. Carbon can be fused into neon, sodium, and magnesium. The star, once again, is granted a state of execution. This pattern is what defines the death of a massive star. Each fusion stage burns a heavier element than the last. Each stage requires higher temperatures. Each stage releases less energy per reaction. As a result, each stage is dramatically shorter than the one before it. Carbon burning in a massive stellar core might last a few hundred years. Neon burning might last 1 year. Oxygen burning might last a few months. And the final stage, silicon burning, lasts only about 1 day. That number deserves a pause. 1 day. A star that has existed for millions of years, that has burned hydrogen for eons and helium for hundreds of thousands of years, now enters its final fusion stage and burns through it in 24 hours. Think about what the star does not know at that point. It has no idea it is in the last day of its life. It has no way of anticipating what comes next. It is simply doing what stars do, converting one element into another, holding gravity at bay. It has run this trick many times before. There is no reason, from the star's perspective, to think this time will be different. But it is different, because silicon burning produces iron. And iron is where the trick stops working. To understand why iron ends everything, you have to understand something about how fusion actually generates power in the first place. When 2 light nuclei fuse together, the resulting nucleus is slightly less massive than the sum of its parts. That missing mass has been converted directly into energy, in accordance with Einstein's famous equation. This is how the sun shines. Every second, our sun converts about 600 million tons of hydrogen into helium, and about 4 million tons of that mass disappears entirely, transformed into pure energy that streams out as sunlight. This trick works because up to a certain point, heavier nuclei are more tightly bound than lighter ones. Fusing 2 light nuclei into a heavier one releases some of that binding energy. The heavier nucleus sits in a lower energy state, and the difference has to go somewhere. That is where sunlight and starlight and every erg of energy from every star that has ever existed comes from. But this only works up to a point, and that point is iron. Iron is the most tightly bound nucleus that stable fusion can produce. If you try to fuse iron with anything else, the resulting nucleus is not more tightly bound. It is less tightly bound. You have to put energy into making the reaction happen. There is no net energy to be gained by fusing iron. It is the ash of nuclear burning, the endpoint that no ordinary star can go beyond by conventional means. So when a massive star, in the final day of its life, begins producing iron in its core, it is producing a substance it cannot burn. The iron builds up, it has nowhere to go, and every second, more of it accumulates. By this stage, the star has developed a structure that looks something like an onion. The layers are set. On the outside, there is still a shell of hydrogen, being lazily fused into helium the way our sun does today. Below that is a shell of helium being fused into carbon and oxygen. Below that, carbon is being fused into neon and magnesium. Below that, neon into oxygen. Below that, oxygen into silicon. And at the very center, wrapped inside all of those layers, sits a silicon-burning shell curled around a growing iron core. Each shell burns hotter, faster, and heavier than the one above it. Each shell is a distinct thermodynamic zone with its own temperature, its own density, its own fusion products. And together, they form a nested structure of layered nuclear furnaces, all feeding the growing pile of iron at the center that cannot be burned. The star, from the outside, still looks like a star. Its surface is enormous. If we replaced our sun with a red supergiant of this type, its outer surface might extend past the orbit of Mars. Its light still streams outward. Anyone looking at it from a distant planet in another star system would see nothing unusual. They might see a stable, if very large and very old, star. They would have no way of knowing that the object in their sky is one day away from ending its existence. But that outward appearance is a lie. Everything the star looks like on the outside is millions of kilometers away from what is actually happening deep in the core. The core of the star, on the inside, is a ball of iron, and it is doing something no other stellar core has ever done before. It is failing. Here is the central mystery this whole story revolves around. A star holds itself up because it is producing energy in its core. That energy exerts pressure. That pressure fights gravity. As long as the fusion continues, the star stays inflated. But once the core switches over to iron, fusion no longer produces net energy. The pressure at the center is now coming almost entirely from the sheer heat and degeneracy of the material itself, not from ongoing reactions. And that pressure has a ceiling. It is not infinite. The iron core can only support itself up to a certain critical mass. That mass is known as the Chandrasekhar limit. And for a hot, rotating iron core in this situation, it works out to somewhere around 1 4/10 solar masses. If the core exceeds that limit, and it will, it cannot hold itself up any longer. What happens next has to be described carefully, because two things go wrong at almost the same instant, and they feed on each other. The first thing that goes wrong is called electron capture. Deep inside the iron core, the material is so dense that electrons are packed against protons at close to nuclear distances. Under enough pressure, an electron will simply merge with a proton, converting it into a neutron and releasing a small particle called a neutrino. That neutrino, being famously difficult to interact with anything, streams out of the star at nearly the speed of light and takes its energy with it. Now, here is why this matters. The core has been supporting itself, in part, through what is called electron degeneracy pressure. That is a strange quantum effect based on the rule that no two electrons can occupy the same state at the same time. So a dense sea of electrons resist being compressed. When you convert electrons into neutrons through electron capture, you remove electrons from that sea. You reduce the very pressure that has been holding the core up. The second thing that goes wrong is called photodisintegration. The temperature at the center of the collapsing core has by now climbed to about 10 billion degrees. At that temperature, the photons of light bouncing around inside the core are so energetic that when one strikes an iron nucleus, it can shatter it. Iron gets broken back down into helium nuclei and free neutrons. This process consumes energy. It absorbs heat from the core, and once again, it saps the very pressure that has been keeping the star inflated. Between those two effects, the iron core loses its ability to hold itself up in a fraction of a second. And then gravity, which has been patiently waiting for this moment for the entire life of the star, finally wins. The iron core begins to fall, and it does not fall slowly. It falls at speeds approaching 1/4 of the speed of light. In less than 1 second, an object roughly the size of the Earth's moon has collapsed into an object roughly the size of a large city. This is the moment the paradox begins, because up here at the surface of the star, 500 million kilometers away, nothing has changed yet. The star still looks like a star. It is still shining exactly the way it was shining yesterday and the day before. Its outer layers, the vast puffy envelope of hydrogen and helium, and all the intermediate elements have absolutely no idea that the center has just fallen out of them. The information about the collapse cannot travel faster than the speed of light, and even at the speed of light, it will take time to reach the surface. A red supergiant of this kind might have a radius of 500 million kilometers or more. Light itself would need almost half an hour just to cross it. The outer layers of the star are completely oblivious to their own doom. Meanwhile, in the center, in a region less than 100 kilometers across, something extraordinary is unfolding. The falling iron and its fragments are being crushed together with such force that the neutrons in the material are pressed against each other until they touch. This is a state of matter no laboratory on Earth has ever produced or ever will produce. It is denser than anything most people can visualize. A single teaspoon of it would weigh more than every human being on Earth combined. When matter is packed this tightly, a new form of pressure kicks in. It is called neutron degeneracy pressure, and like its electron cousin, it comes from a quantum rule that forbids identical particles from occupying the same state. The neutrons resist being pushed any closer together. That resistance slams the brakes on the collapse. The collapsing core suddenly finds itself stopped. Not stopped gently, but stopped like a truck hitting a wall at highway speed. In the very center, a new object has formed. It is called a proto-neutron star. It's about the size of a small city, perhaps 20 kilometers across. It contains more mass than our sun, and it is unimaginably hot, easily 100 billion degrees at its center, hotter than the core of any star that has ever existed under normal circumstances. For a brief moment, this new proto-neutron star holds together. Its structure is being propped up by 4 separate things all working at once. There is the neutron degeneracy pressure we just described. There is thermal pressure, the sheer heat of the object trying to expand it outward. There is the pressure of trapped neutrinos, so many of them being produced by the collapse that even a particle famous for passing through everything gets briefly bottled up inside the dense material. And there is rotation, because as the core collapsed, its spin sped up dramatically. The way a figure skater spins faster when they pull their arms in. That rotation exerts an outward centrifugal effect that adds to the support. Between these four contributions, the proto-neutron star can hold itself together, for now. And that phrase, for now, is where our story really turns. Because here is the question that will decide everything about what happens next. Is the proto-neutron star's support sufficient? Not just for this moment, but for the seconds and minutes and hours to come, as more material continues to rain down from the collapsing layers above? Because make no mistake, the collapse of the core does not stop just because the very center has hit a wall. The layers of silicon, oxygen, and neon that were sitting just above the iron core are also falling inward now, and they are going to hit the proto-neutron star hard. That question does not have a single clean answer. It depends on how much mass is falling. It depends on how fast the star was rotating. It depends on the exact nature of the ultra-dense material inside the proto-neutron star, which is something physicists still cannot fully calculate. There is a maximum mass a neutron star can support before its own pressure fails. Estimates place it somewhere between 2 and 2.5 times the mass of our Sun. But the exact value is one of the great open questions of modern physics. It depends on properties of matter densities we cannot reproduce in any experiment, at temperatures we cannot generate in any facility, and it depends on physics that lies at the very frontier of what human beings currently understand. If the newly formed proto-neutron star is safely below that limit, and if the surrounding conditions are favourable, then it may survive. It may become a stable neutron star, and the star around it may go on to explode as a classic supernova. And this particular collapse story ends there. But if the core was too massive to begin with, or if enough additional material falls onto the proto-neutron star from above, then no combination of pressures will be enough. Neutron degeneracy pressure has a ceiling. Thermal pressure fades as the object cools. Trapped neutrinos leak away. Rotation, however fast, has its limits. The proto-neutron star can be pushed past the point where any known force in the universe can hold it up. And when that happens, when the last support finally gives way, the object collapses again. This time, there is nothing to catch it. There is no known form of matter that can withstand the gravity of a proto-neutron star crossing that threshold. It falls inward on itself, and it keeps falling, and space and time bend more and more sharply around it, until finally an event horizon closes around the material and seals it off from the rest of the universe forever. At that instant, a black hole formed inside the star. But remember where we are. We are still deep in the center of a massive stellar corpse whose outer layers do not yet know what has happened. The event horizon that just formed is tiny by stellar standards, only a few kilometers across. Around it, for millions of kilometers in every direction, there is still a star. Still hydrogen, still helium, still the burning shells that were feeding heavier and heavier elements down into the doomed core. All of it from the outside still looks perfectly ordinary. All of it is still shining, and all of it now surrounds a hole in reality. This is the strange, almost impossible sounding truth that this whole story is built on. A single object can be a black hole at its center and a giant star everywhere else. At the same time, in the same place, for a period that might last seconds or hours, or in some models, even longer. What happens to the rest of the star during that window depends entirely on details we have not yet touched. The rotation of the collapsing material, the way magnetic fields thread through the star, whether an outward shock ever manages to escape, whether infalling matter forms a disk, where the jets punch out from the newborn black hole, whether the outer layers simply fall silently into the void that has opened underneath them. All of that is what comes next. But first, we have to understand exactly what happens in the seconds immediately after the event horizon forms, because the details of that specific window are where the strangest physics of all comes into play. This is where the story of how a black hole gets born inside a star that is still trying to be a star truly begins. So let us return to that instant. The core has collapsed. The proto-neutron star has formed. And now, in a window of time that no human being will ever directly observe, one of two things is about to happen. Either the star will find a way to explode outward, or it will find a way to swallow itself. And in some of the most dramatic cases, it will do both in that order, with the black hole appearing before the surface of the star has any idea what is going on. To understand this window, we have to look at what happens at the exact moment the collapse stops. Because when that infalling core slams into itself and neutron degeneracy pressure suddenly takes over, the collapse does not just halt, it rebounds. The material at the very center, having crashed to a stop, springs back outward slightly. It is a small movement, cosmically speaking, only a few kilometers, but it happened so violently that it launches a shockwave. That shockwave begins traveling outward through the rest of the collapsing material, moving against the tide of matter that is still falling inward from above. For decades, astronomers hoped this shockwave would be the answer to everything. Here, they thought, was the mechanism by which a dying star explodes. The core bounces, a shock travels outward, it plows through the outer layers of the star. Eventually it breaks through the surface and the star lights up as a supernova visible across the galaxy. Simple, elegant, complete. But when they actually tried to model it, the shockwave failed. Not in every simulation, but in most of them. It failed for a very specific reason, and understanding that reason is the key to understanding how a black hole can form inside a star before any explosion has escaped. Here is what happens. The shockwave, as it moves outward through the infalling matter, encounters heavy nuclei that have not yet been ripped apart by the collapse. These are iron and silicon and other atoms that were sitting in the layers above the core when everything started to fall. As the shock passes through them, it deposits energy into them, and that energy breaks them apart into their constituent protons and neutrons. This process is called photodisintegration, and we saw it earlier when the core itself was falling. Now it happens again, this time to the shock wave. Every time the shock breaks apart a nucleus, it costs energy. A lot of energy. The binding energy that was released when those nuclei originally formed through fusion over the star's entire life has to be paid back all at once. The shock is being asked to reverse in a fraction of a second the work of 1 million years of stellar burning. And it does not have the energy to spare. Within milliseconds, the shock has lost most of its outward momentum. It stalls, it stops moving, it just sits there, suspended somewhere inside the collapsing core, while matter continues to rain down onto it from above and get piled onto the proto-neutron star below. Let me slow down on what photodisintegration actually is, because it is one of the strangest and most consequential processes in stellar physics, and it deserves to be understood properly. When we say the shock breaks apart heavy nuclei, we mean something very specific. A nucleus of iron contains 56 particles bound together, 26 protons and 30 neutrons. held in a configuration that took the star its entire life to build. Each of those particles is bound to the others by the strong nuclear force. That binding over billions of individual fusion reactions in the star's core released the energy that made the star shine. Now, in the space of milliseconds, that binding is being undone. A photon of light, when it has enough energy, can strike an iron nucleus and shatter it into 13 helium nuclei and 4 free neutrons. Then those helium nuclei themselves get broken apart into their constituent protons and neutrons. In the space of the collapse, the star is reversing the fusion work of its entire lifetime. And the energy required to undo this fusion work has to come from somewhere. It comes from the shock. Every nucleus the shock passes through and breaks apart takes a bite out of the shock's kinetic energy. And there are a lot of nuclei. The mass of the iron core alone is more than the mass of our sun, and the layers of silicon and oxygen just above it add more still. To photodisintegrate all of that material would require roughly 10 to the 51st ergs of energy. That number is written as a 1 followed by 51 zeros of ergs. It is comparable to the entire energy the sun will radiate over its 10 billion year lifetime, all of which the shock would have to deliver in a fraction of a second. The shock does not have that much energy to spare. Its own energy is comparable to what photodisintegration would consume, not vastly greater. So the shock cannot cleanly overcome the barrier while also driving forward. It gets a small fraction of the way through the infalling material, and its energy runs out. It stalls. This is why the initial rebound cannot, on its own, drive a supernova. The physics simply does not permit it. The bounce is real. The shock is real. But the amount of energy locked up in the nuclear structure of the surrounding material is so vast that it drains the shock before it has traveled any significant distance. Something else has to help. Something has to inject additional energy into the region behind the stalled shock, and that is where the neutrinos come in. This is the moment when everything hangs in the balance. The shock has failed. The star is teetering, and if nothing revives that shock, the game is over. For decades, the leading candidate for what could revive it has been neutrinos. Remember, the collapsing core has been producing an unimaginable flood of neutrinos, and the newly formed proto-neutron star is still producing them at a rate that dwarfs anything else in the universe at that moment. For about 10 seconds, a proto-neutron star radiates more energy and neutrinos than every other star in the observable universe combined. It is one of the most powerful sources of energy known to physics. Now, neutrinos are famously reluctant to interact with anything. Trillions of them are passing through your body every second from the sun, and you never notice, because they almost never bump into anything. But the density inside a collapsing star is so extreme that even neutrinos in this environment have a chance of being absorbed. And if enough of them are absorbed by the material just behind the stalled shock, they deposit enough heat to re-energize it. The shock lurches forward again. It gets a second chance to punch outward through the star. This is the neutrino heating mechanism, and it is currently the leading explanation for how ordinary core collapse supernovae successfully explode. When it works, the outer layers of the star get unbound and blown into space. A neutron star is left behind at the center. A bright supernova lights up the sky. But here is the critical thing to understand. It does not always work. Sometimes the neutrinos are not efficient enough. Sometimes the geometry is wrong. Sometimes there is simply too much matter falling in from above. for the shock to overcome, no matter how much heat gets deposited behind it. And when it does not work, when the shock cannot be revived, the story takes a very different turn. I want to be honest with you here about something important. The exact details of how successful supernova explosions happen are still an active area of research. Simulations of the neutrino-driven mechanism have gotten better and better, and many of them do now produce successful explosions, but there are still open questions about the role of convection, of turbulence, of rotation, of magnetic fields. The picture I am painting is our best current understanding, but it is not fully settled science. Different research groups get slightly different answers depending on the assumptions in their models. What everyone agrees on, though, is that the failure mode, the case where the shock never revives, is a real possibility, and it is central to what we are exploring. Now let me describe the proto-neutron star itself, because in the middle of all this violence, this object briefly exists as one of the most extreme structures in the universe, and its physical properties are worth pausing on. Imagine a sphere roughly 20 kilometers across, containing more mass than our Sun. The gravity at its surface is so intense that the escape velocity approaches half the speed of light. The temperature at its core is around 100 billion degrees, which is hotter than any environment in the cosmos, except for the interiors of stellar explosions themselves. The pressure at its center exceeds 10 to the 29th times the atmospheric pressure at sea level on Earth. And it is spinning. It is spinning fast. As the original core collapsed by a factor of thousands in radius, its rotation rate sped up by the same factor squared, following the conservation of angular momentum. A core that was originally turning once every few days is now turning once every few seconds, and in the most rapidly rotating cases, once every few milliseconds. The composition of this object is unlike anything else in the universe. In its outer layers, the density is around that of ordinary atomic nuclei, and the material consists of neutrons packed together with a small admixture of protons and electrons. Deeper in, the density climbs by factors of 10 and more, and the material begins to do things that no laboratory can reproduce. Some models predict that quarks, which are normally confined inside protons and neutrons, may become free and form a strange kind of quark matter. Other models predict exotic particles called hyperons appearing in the mix, containing quarks that do not exist in ordinary matter. Still others predict a phase transition to something called a color superconductor, in which quarks pair up in a manner analogous to the electron pairs that produce ordinary superconductivity, but with an entirely different set of properties. We do not know which of these is correct. Different models predict different behavior, and until we can observe the interior of a neutron star directly, which we cannot say for sure. This is why the equation of state matters so much. It is the mathematical bridge between the density of the material and the pressure it exerts. And getting it wrong means getting the maximum mass wrong. If quark matter appears at high densities and softens the pressure, the maximum mass is lower and more collapses end as black holes. If the pressure stays high all the way up to extreme densities, the maximum mass is higher and more collapses end as stable neutron stars. This difference is not academic. It determines whether a given collapse produces a neutron star that will still be shining a billion years from now, or a black hole that sealed itself off from the universe in a fraction of a second. And we still do not know which answer nature actually gives. Because if the shock fails and is never revived, then nothing is stopping the material above from continuing to fall onto the proto-neutron star. And as more mass piles onto that already dense object, its own gravity intensifies. The proto-neutron star is being loaded like a scale that already has too much weight on it. There are two paths from here to a black hole. The first is what we call prompt collapse. In this scenario, the core that collapsed in the first place was so massive that even the initial formation of the proto-neutron star cannot resist the crush of gravity. Neutron degeneracy pressure, thermal pressure, trapped neutrinos, rotation, everything combined, still is not enough. The proto-neutron star exists for only a few milliseconds before it collapses again, and this time, no known force can stop it. An event horizon closes around it almost immediately. The black hole is born within a heartbeat of the core collapse itself. The second path is delayed collapse. Here, the proto-neutron star does manage to hold itself up initially. It exists as a stable, hot, spinning object for some length of time. Maybe half a second, maybe a full second, maybe even a few seconds. During that window, it looks briefly like the star might just leave behind a neutron star and be done with it. But then more material continues to accrete onto it from above, and its mass climbs and climbs and climbs, and eventually it crosses whatever the true maximum neutron star mass turns out to be. At that point, all of its support gives way at once, and it collapses into a black hole almost instantly. Prompt and delayed collapse can look very different, but they share a fundamental feature. In both cases, the event horizon forms deep inside a star, whose outer layers are still completely intact. And this is where we need to pause and really think about what that means. The event horizon that just formed is small, extraordinarily small, by stellar standards. For a black hole with a mass of about 3 solar masses, the event horizon has a radius of only about 9 kilometers. 9 kilometers. That is smaller than most cities. The event horizon of a 10 solar mass black hole has a radius of only about 30 kilometers. And around this tiny region of sealed off space and time, the star continues to exist. The layers of silicon, oxygen, neon, carbon, helium, and hydrogen that were arranged around the original iron core are all still there. They stretch outward for hundreds of thousands, or even millions of kilometers. They are still doing what they were doing before. The hydrogen envelope is still shining, the surface of the star is still emitting light. This is the central strangeness of the whole phenomenon, and it deserves a careful look, because it violates our intuition in a way that is almost impossible to shake. When we think about a star dying, we picture something dramatic, a flash, an explosion, a visible event. But at the moment the event horizon forms deep in the core, none of that is happening at the surface. The surface has no idea. It cannot possibly know. The information that the core is gone, that the very center of the star is now a black hole, is traveling outward at the speed of light. And even light needs time to cross a star that big. Let me put some numbers on this. A red supergiant progenitor for this kind of collapse might have a radius of about 500 million kilometers. Light takes about half an hour to cross that distance. So if a black hole forms in the very center of that star at, let us say, 12 o'clock noon, the information that the black hole formed cannot possibly reach the surface until about 12:30. For a full half hour after the event horizon closes, the star's surface is still shining exactly the way it was shining before, completely oblivious to what has happened deep inside. But it is worse than that, because a shock wave, even a successful one, does not travel at the speed of light. It travels much more slowly. A shock through the interior of a massive star might move at a few percent of the speed of light at best. If the mechanism that revives the shock ever manages to work, it might take hours or even a full day for that shock to actually cross the star and break out of the surface. And that surface breakout is what we would see from Earth as the beginning of a supernova. So in a very real sense, the visible supernova, if there is one, is separated in time from the actual moment of core collapse by hours or more. The black hole, if it forms, exists long before the star lights up. This has enormous consequences for how we think about what we observe. When astronomers say that a supernova exploded on a certain night, what they mean is that the light from the shock breakout or from the material just behind the shock first reached us on that night. But the collapse of the core happened well before that. And if a black hole formed during that collapse, it has been sitting inside the star, hidden, for whatever length of time it took the shock to travel outward and become visible. That is a stretch of time during which the black hole existed, but was completely invisible from the outside. It was buried inside its own star. Now, is anything at all leaking out of the star during that window? Because if a black hole is forming in the middle of a star, you might think there would be some kind of dramatic signal that could reach us. And there might be. But it is subtle. The most promising signals are neutrinos and gravitational waves. Neutrinos, as we discussed, can pass through matter that would stop everything else. So even though a black hole is forming inside a star with millions of kilometers of overlying material, the neutrinos being produced during the collapse itself can escape almost immediately. They stream out through the star's layers as if they were not there. For a collapse happening in a nearby galaxy, we might be able to detect this neutrino burst directly. In fact, we have. In 1987, a supernova exploded in a nearby small galaxy called the Large Magellanic Cloud, and neutrino detectors on Earth registered a brief burst of neutrinos about 3 hours before the visible light of the supernova arrived. It was a small number of events, only around 24 neutrinos detected in total across all instruments, but it was enough to confirm that yes, neutrinos really do carry information about the collapse itself, and they get to us before the light does. Here is something even more striking, and it is one of the most direct pieces of evidence for what we are describing. If a proto-neutron star is producing a torrent of neutrinos, and then it collapses into a black hole, the event horizon closes around the material that was making those neutrinos in the first place. The moment that happens, the neutrino signal should abruptly cut off, not fade, not decline, cut off, because the source of the neutrinos has just been sealed inside a region from which nothing can escape. If we were to see a collapse where the neutrino signal built up, held steady for a fraction of a second, and then suddenly stopped, that would be a nearly direct signature of a black hole forming inside a star. We do not yet have a confirmed observation of exactly this, because such an event requires a collapse close enough for our current detectors to catch it. But the physics is clear, and next generation neutrino detectors may well be sensitive enough to see this kind of signal when the right collapse happens. That 1987 neutrino detection deserves more attention, because it remains the best real-world example we have of what neutrino astronomy can teach us. The 3 detectors that registered those events sat in Japan, the United States, and Russia, respectively, and the burst arrived over a window lasting only about 13 seconds. But those detections, though sparse, told us extraordinary things. They confirmed, for the first time in history, that our theoretical picture of core collapse was fundamentally correct. Massive stars do collapse. Their cores do produce enormous fluxes of neutrinos. Those neutrinos do carry away the energy of the collapse. All of the general physics we had worked out on paper was confirmed by those 13 seconds of data from one nearby galaxy. The neutrinos also arrived hours before the visible light from the supernova, exactly as the theory predicted, because they were able to stream directly out of the collapsing core, while light had to wait for the shock to reach the surface. It was one of the founding events of neutrino astronomy, and an early example of what has since become the broader field of multi-messenger astronomy, in which information from light, neutrinos, and gravitational waves gets combined to reconstruct what is happening at cosmic distances. But here is the humbling part. That event happened in a satellite galaxy of our own Milky Way. It was, on cosmic scales, right next door. If a similar collapse occurred in a galaxy even 10 times further away, the number of detected neutrinos would drop by a factor of 100, from about 24 to well under 1. We would not see a burst. We would see, at best, a single neutrino, which we could not distinguish from background events. For collapses at truly cosmological distances, in galaxies hundreds of millions of light years away, we cannot detect the neutrino signal at all with current technology. The 1987 event was rare and precious, and we have not seen another supernova neutrino burst since. Massive star deaths in our own galaxy happen only every few decades on average. We are, in a sense, still waiting. Gravitational waves are the other signal that might tell us something. When a massive object undergoes a rapid asymmetric change in shape, it sends ripples through the fabric of space and time. The collapse of a stellar core is exactly that kind of event, or it can be if there is enough asymmetry. A perfectly spherical collapse would not radiate any gravitational waves at all, because the symmetry cancels the signal out. But real collapses are not perfectly spherical. Rotation makes the core bulge. Instabilities cause it to slosh. Convection stirs it up. All of these deviations from perfect symmetry produce gravitational waves, and those waves travel outward at the speed of light, through the star and beyond, as if the star were not even there. The problem is that these gravitational wave signals are much weaker than the ones we routinely detect from merging black holes and neutron stars. Those merger signals come from objects that spend seconds or minutes spiraling around each other before they collide, generating a long, clean waveform that our instruments can pick up. A stellar collapse produces a burst that lasts only a fraction of a second, with a shape that depends heavily on the specific details of the collapse. Detecting such a burst at intergalactic distances is very hard with current technology. For a collapse in a nearby galaxy, we might see it. For collapses in more distant galaxies, we probably would not. But the signal is there. It is being emitted. And when the event horizon forms, when the proto-neutron star finally gives way and collapses into a black hole, the gravitational wave signal is expected to show a characteristic feature. A brief, powerful burst as the object rings down into its final black hole state. Then silence, because a stationary black hole radiates no gravitational waves at all. Now, all of this raises a question that I have been dancing around. Where exactly is the maximum mass that a neutron star can support? because that number, that boundary between the object survives as a neutron star and the object collapses into a black hole, determines which path the collapse takes. And the honest answer is that we do not fully know. What we do know is that it depends on something called the equation of state of ultradense matter. This is a horribly technical sounding phrase, but it means something very specific and important. It means the mathematical relationship between how dense a piece of matter is and how much pressure it exerts. For everyday materials, we understand this relationship well. For water at room temperature or steel at ordinary pressures, we can write down the equation of state exactly. But for matter squeezed to nuclear density and beyond, we cannot. That regime is beyond what any laboratory experiment can access. It involves quantum chromodynamics, the physics of quarks and gluons, in a regime where none of our approximations work very well. And different theoretical models give different answers. Some models predict a maximum neutron star mass of about 2 solar masses. Others predict 2 3/10. A few go as high as 2.5 or so. This might sound like a small range, but it makes an enormous difference for which stars end up as black holes and which end up as neutron stars. And this is why it is one of the great open questions in modern astrophysics. Every time we detect a new neutron star, every time we measure the mass of one accurately, we are chipping away at that uncertainty. Every time we see a merger between 2 neutron stars in gravitational waves, we learn something more about how the material behaves under extreme conditions. Slowly, painfully, we are constraining the equation of state, but it is not settled yet. And until it is, we cannot say precisely where the boundary is. What we can say is this: there is a boundary. It exists. And if the mass of the collapsing core is above it, no combination of pressures will save the proto-neutron star. The event horizon will form. The black hole will be born. And it will be born inside a star that has millions of kilometers of overlying material still going about its business. Let me try to give you a sense of the timeline one more time, because it is genuinely difficult to hold in your head. From the moment silicon burning finishes and the iron core reaches critical mass, the collapse itself takes about 1/10 of a second. In that 1/10 of a second, an Earth-sized ball of iron falls into a city-sized object made of pure nuclear matter. The proto-neutron star, if it forms, exists for anywhere from milliseconds to a few seconds before either stabilizing or collapsing further. If a black hole forms, whether promptly or after a delay, that formation happens within a window of, at most, a few seconds after the initial collapse. Meanwhile, the shock, and if it revives, takes hours to cross the star and reach the surface, and the outer layers of the star remain throughout this entire process, completely undisturbed until the shock arrives. So we have this bizarre situation where the death of the star, in the deepest physical sense, happens in a few seconds. But the star's public performance of dying, the flash of light that we see from Earth as a supernova, does not begin until hours or days later. And in the interim, if things went the way we have been describing, there is a black hole hidden inside the star, and depending on what happens next, it may either be swallowed by the coming explosion, or it may swallow the star, or it may find itself surrounded by a swirling disk of material that starts producing some of the most violent phenomena in the universe. That is where our story goes next. Because it turns out that the fate of the rest of the star, once the black hole exists inside it, is not one story. It is 3. And which one plays out depends on details we have not yet touched. So we now have a picture of what has happened. The core has collapsed. The proto-neutron star has either failed instantly or held on briefly before failing. An event horizon has closed around a region of matter deep inside a star that is still, from the outside, doing what stars do. The black hole exists. And now, over the next seconds and minutes and hours, everything surrounding that new horizon has to decide what it wants to do. This is where the picture really opens up. Because contrary to what you might expect, the formation of a black hole inside a massive star does not lead to a single uniform outcome. It leads to 3 dramatically different fates, and which one plays out depends on details that were set long before the star ever began to collapse. Rotation, mass, the composition of the star, whether it had a partner star that stripped away its outer layers over millions of years. These factors, decided during the star's youth and middle age, determine what happens in these final seconds. Let me walk you through the 3 paths. And I want to be honest that they are not perfectly separate boxes. They form a spectrum. A given collapse might fall between 2 of these outcomes, or produce features of more than one. But the extremes really are strikingly different, and understanding them will make sense of everything else. The first fate is the quietest, and in many ways the most unsettling. It is called a failed supernova. In this scenario, the shock never revives, or if it revives, it does not have the strength to actually unbind the outer layers of the star. Material continues to fall inward. The proto-neutron star, if one formed at all, is overwhelmed. A black hole appears at the center, and then, over the course of hours to days, the rest of the star simply falls into it. Not explodes, not lights up, falls. Think about what that means for a moment. A star that has been shining for millions of years, that has been visible in some distant galaxy as a bright red or blue point of light, simply stops being there. From the outside, if you were watching that star through a telescope, you would see it dim and dim and dim, and then it would be gone. There would be no explosion. There would be no supernova. There would just be an absence where a star used to be. For a long time, the possibility of failed supernovae was mostly theoretical. Physicists had run simulations and found that in some cases, the shock never made it out and the star just fell into the newly formed black hole. But there was no direct observational evidence that this was actually happening in the real universe. It seemed like the kind of thing that ought to be very rare, if it happened at all. Every massive star we saw dying seemed to die as a supernova, at least the ones we caught. That changed when astronomers started specifically hunting for stars that disappeared without an explosion. There have been surveys designed to monitor massive stars in nearby galaxies, taking images over years and looking for any of those stars that vanish without a supernova. It is painstaking work, because it requires rule out the possibility that the star simply dimmed for other reasons, or was obscured by dust, or moved out of the field of view. But a few candidates have turned up. Stars that appear to have been there in one image, and then in later images, are simply not there anymore, with no supernova ever recorded in between. I want to be careful here because none of these observations are conclusive. The interpretation that these represent stars falling directly into black holes without exploding is the leading explanation, but it is not the only possible one, and the total number of good candidates is small. What the observations do suggest is that this kind of quiet stellar death does happen, and it may not even be all that rare. Some estimates suggest that a significant fraction, perhaps 10 or 20%, of the most massive stars end their lives this way rather than as visible supernovae. But those numbers are uncertain, and they depend heavily on which models you trust. Now I said quiet, and I meant it, but I need to add a caveat. A failed supernova is not necessarily completely dark. Even when the shock fails and the material mostly falls in, there can still be signals. As the outer envelope of the star begins to fall inward, it may produce a brief, weak transient, a dim brightening of the star that lasts a few days or weeks before it fades to nothing. There can be radiation from material heating up as it falls onto the growing black hole. There can be a burst of neutrinos even in the failed case because the initial collapse still produces them. And there is a subtle effect that gets discussed in the literature about how the star loses mass to neutrino emission during the collapse. Even if no other explosion happens, that lost mass changes the gravitational binding of the outer layers, and the outer envelope, no longer as tightly held, may undergo mild rearrangement that produces its own faint signal. So, the picture of the failed supernova is not star goes dark instantly and forever. It is more like star fades over a few weeks, produces a weak flicker that could easily be missed, and then vanishes from view, leaving behind a black hole that has slowly eaten most of its own progenitor. That is a strange and haunting kind of death. It is a death without a funeral. The second fate is more familiar in some ways, but it hides a strange twist. It is called fallback collapse, and it involves a weak explosion followed by material sagging back down onto the remnant. Here, the shock does revive, at least somewhat. The neutrino heating mechanism, or something like it, manages to push the shock outward, and it makes its way through the star. Some of the outer layers do get unbound. A supernova does occur. From the outside, if you were watching, you would see a genuine explosion. A star would brighten dramatically. A visible supernova would appear in the sky. Everything would look at first like a normal core collapse supernova, but not all of the material that gets pushed outward actually reaches escape velocity. Some of it, particularly the innermost layers, is only weakly unbound. It goes outward for a while, slows down, stops, and then begins to fall back. This is the fallback part of fallback collapse. Material that seemed to be ejected finds that it did not have quite enough energy to make it out, and it comes home. When it comes home, it lands on whatever compact remnant was left behind by the initial explosion. In many cases, that remnant is a proto-neutron star. And here is where the twist happens. The proto-neutron star, having survived the initial collapse, is now being loaded with additional mass from all the material falling back onto it. It may have been safely below the maximum neutron star mass at first, but as fallback accumulates, its mass climbs. Eventually, if enough material falls back, it crosses the threshold. And then, hours or even days after the original supernova, the proto-neutron star collapses into a black hole. Think about the strangeness of that sequence. From Earth, we would see a supernova. It would be a normal-looking supernova, or maybe a slightly odd one, but a supernova nonetheless. It would brighten, peak, and start to fade over the following weeks. And meanwhile, somewhere in the middle of it all, hidden by the expanding envelope of ejected material, a neutron star that was just born would have quietly transformed into a black hole, because it kept accumulating fallback long after the visible fireworks began. There would be no obvious external signal of this second collapse. The supernova would just continue declining as expected, but the compact object at the center would no longer be a neutron star. It would be a black hole. This is one of the reasons why the relationship between supernova and compact remnant is more complicated than it might seem. You cannot always tell from the visible supernova alone what was left behind. In many cases, we assume that a bright core collapse supernova leaves a neutron star, and often it does, but sometimes it leaves a black hole because fallback finished the job that the initial collapse could not. And distinguishing those two cases from Earth, based on the supernova light alone, is very difficult. Fallback collapse is also important because it gives us a natural way to make black holes with masses that fall in what astronomers call the mass gap. Neutron stars have a maximum mass of somewhere around 2 or 2.5 solar masses. Stellar mass black holes are often observed with masses of 5 solar masses or more. There has historically seemed to be a shortage of compact objects with masses in between, from about 2 to about 5 solar masses. Fallback collapse provides a natural way to fill in that region, or at least to explain why some black holes have masses that are only a little bit above the neutron star limit. A little bit of fallback pushes a proto-neutron star just over the edge, producing a black hole that is not much heavier than the neutron star it started as. A lot of fallback produces a heavier black hole. The amount of fallback controls the mass of the resulting black hole in a fairly direct way. Now we come to the third fate, and this is where things get truly dramatic. It is called the collapsar, and it is the mechanism that many astronomers now believe is responsible for some of the most energetic explosions in the universe. If failed supernovae are the quietest deaths, and fallback collapses are somewhere in the middle, collapses are the ones that scream. They involve black holes that form inside stars, and then, instead of quietly swallowing everything, launch beams of matter and energy that punch through the star at nearly the speed of light and light, up the sky from billions of light years away. The collapsar model starts with a very specific kind of progenitor. It requires a massive star, yes, but not just any massive star. It requires one that is spinning at exceptional rates. Most massive stars do not rotate that fast, or if they did in their youth, they lost most of their spin to stellar winds over the course of their lives. So a collapsar progenitor is a special kind of object. It needs to have kept most of its rotational energy right up until the moment of collapse. Why does rotation matter so much? Because when a rotating star collapses, its material cannot all fall directly to the center. Some of it has too much angular momentum. It is spinning too fast to fall straight in. Instead, it settles into a disk around the newly formed black hole. The way water going down a drain forms a swirling vortex, rather than plunging straight down. This disk, called an accretion disk, becomes the engine that powers everything that follows. Accretion disks around black holes are astonishing structures. As material spirals inward, it gets squeezed and heated by friction with itself. Temperatures in the innermost regions of the disk can reach tens of billions of degrees. The material becomes intensely luminous, and gravitational energy from the infall gets converted into radiation and outward motion with remarkable efficiency. A significant fraction of the rest mass energy of the infalling material, sometimes several percent, can be extracted as usable energy. To put that in perspective, nuclear fusion, which powers stars, extracts only about 0.7% of the rest mass of hydrogen. Accretion onto a rapidly rotating black hole can extract 10 times as much energy per unit mass or more. It is the most efficient energy release process in the known universe, short of matter-antimatter annihilation. So we have a rapidly rotating stellar core that has collapsed. A black hole has formed. Instead of everything falling straight in, an accretion disk has formed around the black hole. That disk is unimaginably hot. It is threaded with strong magnetic fields because the collapsing material dragged its magnetic fields down with it and amplified them. And through mechanisms that are still being worked out in detail, but which likely involve the interplay of that magnetic field with the spin of the black hole itself, energy starts to be pumped outward along the rotation axis of the system. Not just any energy, a collimated beam of energy and matter traveling at speeds so close to the speed of light that they are almost indistinguishable from it. These are relativistic jets, and they are among the most powerful phenomena in the universe. The jets begin at the accretion disk. They are launched along the poles, perpendicular to the disk, and they start driving outward through the star. Remember, all of this is happening inside a star. The black hole is buried under millions of kilometers of stellar material. The jets have to force their way out, and this is not a gentle process. The jets carry enormous energy. They shove aside everything in their path. They cut through the layers of the star like a laser slicing through paper. If the star is right for it, the jets make it all the way through. They emerge from the surface of the star, moving at nearly the speed of light. And now they are in open space, and they can do what jets do. They plow into the surrounding interstellar medium. They produce shock fronts. They accelerate particles to extraordinary energies. And they generate radiation across the electromagnetic spectrum, including a spectacular burst of gamma rays that can be detected from billions of light years away. This is where astronomers believe long-duration gamma-ray bursts come from. These are among the most energetic events in the universe. A single gamma-ray burst can release in a few seconds an amount of energy comparable to what the sun will release across its entire 10 billion year lifetime. And if you happen to be positioned within the narrow cone of the jet, the burst appears thousands of times more brilliant still because all that energy is beamed in your direction. That energy, funneled through relativistic jets emerging from the death of a rapidly rotating massive star, produces a signal that our satellites can pick up from most of the observable universe. I want to be careful with the language here though. Not every long-duration gamma-ray burst is definitely produced by exactly this mechanism. The collapsar model is the leading explanation, and it fits a lot of the observations, but the central engine of a gamma-ray burst is hidden from direct view, and there are open questions about the details. Different bursts may have somewhat different central engines. Some may involve slightly different variations on the collapsar theme. The strongest conclusion we can defend is that many, and probably most, long-duration gamma-ray bursts come from the deaths of massive stars, and that the collapsar mechanism, in some form, is the leading candidate for producing them. The collapsar model also connects to what astronomers call hypernovae, sometimes classified as unusually energetic broad-lined supernovae of a particular type. These are core collapse supernovae, whose explosions are much more energetic than normal, sometimes 10 times as energetic. They tend to be associated with stripped stars, stars that have lost their outer hydrogen envelopes, and they sometimes coincide with long-duration gamma-ray bursts. The connection is not perfect. Not every hypernova produces a gamma-ray burst, and not every gamma-ray burst has a clearly detected hypernova alongside it. But the association is strong enough that many astronomers believe the same basic engine, a rapidly spinning black hole with an accretion disk and jets, is responsible for both. And here is the really striking thing. In the collapsar scenario, the black hole forms first. The jets come from the black hole. The energy powering the visible explosion, if there is one, comes from accretion onto the black hole and from the winds and jets that this accretion produces. The black hole is not the aftermath of the explosion, it is the source of it. The star does not blow up and then collapse, it collapses and then blows up, driven by the black hole that has just been born inside it. This is a genuinely counterintuitive picture. It reverses the usual causal order. For most of the history of astrophysics, we have thought about supernovae as explosions that happen first, with compact remnants being what is left behind afterward. In the collapsar case, the remnant comes first, and the explosion is powered by processes that involve that remnant. The black hole is not the ash, it is the engine. Now, I said earlier that these three fates form a spectrum. Let me come back to that, because the boundaries between them are not sharp, and there are intermediate cases and edge cases and combinations that make the whole picture much richer than three neat categories. Consider a rapidly rotating massive star that forms a black hole and an accretion disk, and starts trying to launch jets, but the jets do not quite make it through the star. This can happen if the outer envelope of the star is too thick, or if the jets are too weak, or if the star's structure is not favourable. In this case, the jets deposit their energy inside the star rather than escaping. They still stir things up. They still add energy to the surrounding material, and that deposited energy may help unbind the outer layers of the star, producing a bright explosion, but it does not produce a classical gamma-ray burst because the jet never made it out. This is called a choked jet scenario. The star still explodes, and it may look somewhat similar to a hypernova from the outside, but there is no gamma-ray burst signature because the jet was contained. Or consider a case where the jets do make it out, but the star's original outer layers are still mostly intact. If a red supergiant with a thick hydrogen envelope tries to produce a collapsar-style event, the jets have a very hard time punching through all that material. They may succeed, but only after depositing enormous energy inside the star, which contributes to the visible explosion. Or they may fail entirely and choke. This is one of the reasons why gamma-ray bursts are more strongly associated with stripped stars than with hydrogen-rich supergiants. The compact, hydrogen-stripped progenitor gives the jets a much easier time getting out. And then, there is the question of what rapidly rotating even means for a stellar core. Most massive stars are not born spinning fast enough to produce a collapsar. Even if they were, stellar winds carry away angular momentum over the course of their lives. A star that started with a fast rotating core might slow down significantly before it collapses. The stars that seem most favourable for collapsar events are ones that avoided too much wind loss. Low metallicity stars, meaning stars with a small fraction of heavy elements, tend to have weaker winds, because heavy elements are what makes stellar wind strong. So low metallicity stars can retain more mass and more angular momentum, making them more likely to end their lives with the fast spinning cores needed for a collapsar. Binary interactions matter too. If a massive star has a close companion, various interactions can strip away its outer layers, leaving behind a compact, stripped core. This kind of stripping can also spin the star up in some cases, or preserve its rotation. Some collapsar candidates are thought to have gone through binary interactions of this kind. On the other hand, binary evolution can also slow a star down. It depends on the specifics. There is one more ingredient worth mentioning before we leave the collapsar picture. And that is what those amplified magnetic fields actually do once the black hole has formed. The strengths they reach after compression are almost unimaginable, potentially trillions of times stronger than the magnetic field of the Earth. Around a newborn, rapidly spinning black hole, these amplified fields become active participants in the physics rather than passive features of the environment. They may help extract rotational energy from the black hole itself through a process that couples the spin of the horizon to the surrounding magnetized plasma. They may collimate the outflow from the accretion disk into the narrow jets we observe. They may determine in part whether a jet succeeds or chokes. The exact details of how magnetic fields interact with a spinning black hole and its accretion disk are still being worked out in modern simulations, but the general point is clear. A collapser is not just a black hole with a disk. It is a black hole with a disk threaded by extreme magnetic fields, and those fields are essential to the show. Without them, the black hole would consume matter silently. With them, the collapse becomes visible from distances measured in billions of light years. So when we ask, what fate will a given massive star meet? The answer is not just about the mass at collapse. It is about a whole family of details. How much mass? How much rotation? What is the metallicity? Did it have a companion? Did that companion strip it? What is the structure of its final onion-layered core? These factors combine to determine which of the three fates plays out, and where along the spectrum the particular collapse falls. That variability is part of what makes this whole subject so rich. If every black hole forming collapse produced the same thing, the astronomy would be much simpler. But instead, we get this diverse zoo of outcomes. Some stars die in silence, their light fading to nothing while a black hole gently swallows them. Some stars explode with reasonable brightness, but their neutron stars sag into black holes as fallback catches up. And some stars produce the most energetic explosions the universe knows about, with beams of matter and energy driven by black holes that were born only seconds earlier and are already commanding the show. Three fates, one underlying phenomenon. A black hole forms inside a still existing star, and what happens next depends on the star's own history and structure. Now we turn to what we can actually see from Earth, because all of this is happening at distances measured in millions or billions of light years, and figuring out which fate a given collapse met, based only on the signals that reach us, is one of the great challenges of modern astronomy. Everything we have described up to this point is happening at distances so vast that no human being will ever see it up close. The nearest galaxy where a massive star collapse might be occurring right now is beyond the reach of any spacecraft we will ever build. The signals from these events travel across those distances for millions of years before reaching us, and by the time they arrive, they are faint, filtered, and often difficult to interpret. And yet, from those signals, we have to figure out what actually happened. We have to work out from a handful of photons and neutrinos, and maybe a ripple in space-time itself, whether a star quietly fell into a black hole, or was blown apart around one, or launched jets that punched out from a newborn horizon. That is among the hardest problems in modern astronomy, and it is where we turn now. Let me start with the most obvious question. If a massive star fails to explode and just falls into a black hole, how do we know? How would we ever detect something whose defining feature is that it does not do the thing we would normally expect it to do? The answer, and this is one of the most beautiful ideas in observational astrophysics, is that we simply watch massive stars in nearby galaxies and look for ones that vanish. That sounds absurd when you first hear it, but it works. Astronomers have been running surveys that monitor the brightest, most massive stars in dozens of nearby galaxies, taking images year after year. In each galaxy, they identify all the massive supergiants they can see, and then they wait. Most of these stars will do nothing over the timescale of a human observing program. Some will eventually explode as supernovae, and we will see the explosion. But if the theoretical picture is right, a fraction of them should simply disappear without producing a supernova. 1 year, the star is there. A few years later, it is not. There has been no bright event in between, no supernova on record, nothing that would explain its absence except the possibility that it has fallen quietly into a black hole. A small number of good candidates have emerged from these surveys. There have been a few red supergiants in galaxies at distances of around 20 million light years or so that appear to have vanished in exactly this way. They were monitored for years, they were catalogued, they were confirmed to be there, and then in follow-up observations, they were gone. Deep imaging with the largest telescopes has failed to find them at their previous positions, and no supernova was reported at those locations during the intervening time. The most natural interpretation is that these stars collapse to form black holes without producing the visible explosions we would normally expect. Let me describe how one of these surveys actually operates, because the observational challenge involved is remarkable. The strategy is to pick a set of nearby galaxies, typically within about 30 million light years, where individual bright stars can be resolved and monitored. In each galaxy, astronomers catalogue the massive, luminous stars they can see, particularly the red supergiants, which are the endpoints of many massive star lives. They then observe those same galaxies repeatedly over years, using large telescopes, taking deep images at multiple wavelengths and comparing them to the catalogue. Most of the time, nothing changes. The stars sit there doing what they were doing. Occasionally one explodes as a supernova, and that shows up dramatically in the difference between 1 year's image and the next. But every so often, an anomaly appears. A star that was clearly present in earlier observations is simply not visible in later ones. It has not exploded, because no supernova was detected at that location by any of the survey networks that continuously monitor the sky. It has not moved. It has not dimmed slightly. It is just gone. At that point, the real work begins. Follow-up observations use the largest available telescopes to look as deeply as possible at the star's former location. If any faint remnant, any lingering material, any residual glow can be detected, it might not be a true disappearance after all. Perhaps the star is hidden behind newly formed dust. Perhaps it is dimmed by many magnitudes but is still there. Perhaps a very faint transient occurred that the initial survey missed. All of these possibilities have to be ruled out one by one, and doing so takes years of careful observation across many wavelengths, especially in the infrared where dust obscuration is reduced. Even after all that work, the conclusion that a star has vanished into a black hole cannot be reached with certainty. It can only be reached by exclusion, by showing that every other explanation is less consistent with the data than the direct collapse hypothesis. A handful of candidates have survived this exclusion process. The first widely discussed one was a red supergiant in a galaxy roughly 26 million light-years away, which appeared to disappear over the course of observations starting around 2009. Since then, additional candidates have emerged from ongoing surveys, though the total number is still small. Each one is precious data, and each one strengthens the case that this quiet mode of stellar death is a real feature of the universe, not just a theoretical possibility. I want to stress again that this is not fully settled. It is possible that these stars are hidden behind newly formed dust, or that they underwent some kind of atmospheric event that dimmed them dramatically without killing them, or that our observations missed a faint transient signal that would have been the signature of a failed collapse. Astronomy is full of surprises, and single object interpretations should always be treated cautiously. But the accumulating evidence, along with the theoretical expectation that some fraction of massive stars must end this way, has moved the failed supernova from a purely theoretical possibility to something that appears to be observationally supported. And now I need to walk back one thing, because it is important. When astronomers talk about a star vanishing, they do not always mean it went completely dark. In some models, a failed collapse produces a weak, brief brightening of the star before it fades. This can happen because when the outer envelope of the star begins to fall inward, some of the material may shock against itself and produce a modest amount of radiation. In other models, there is a subtle glow as material heats up while it accretes onto the newborn black hole. These signals are much weaker than a normal supernova, and they may last only weeks rather than months, but they are not zero. If we happen to catch such a signal and interpret it correctly, we might see it as a strange, dim, brief transient that does not fit into any of our usual categories. It might look like a very faint supernova that never got bright, or a strange stellar outburst, or an anomaly that got flagged as unusual and then forgotten. In fact, some astronomers wonder whether we have already seen a few of these events and misclassified them because we were not sure what we were looking at. Now let me talk about what happens for the two more energetic fates, because the observational signatures there are very different. For fallback collapse, the observational picture is complicated. From our point of view, a fallback collapse looks initially like a normal supernova. We see the light curve rise, we see it peak, we see it fade, and based on that light curve alone, we would probably classify it as an ordinary core collapse event. The transformation from neutron star to black hole, which happens hours or days later as material falls back onto the young remnant, is hidden inside the expanding envelope of ejected material and does not produce any obvious external signal. But there are ways to detect it indirectly. One is by careful analysis of the light curve itself. A supernova powered in part by continued accretion onto a black hole may look slightly different from one where the neutron star just sits there and cools. There can be extra energy input at late times, or unusual features in the way the brightness declines. Another way is by looking for signals from the interaction of ejected material with material that falls back and gets ejected again through processes involving the accretion disk that forms around the newborn black hole. And a third way, ultimately, is by identifying the compact remnant years later. If we can look at the site of an old supernova and find that the remnant is a black hole rather than a neutron star, we can work backward and infer that fallback must have completed the collapse. This kind of forensic work is difficult, but it has been done in a few cases. And it is one of the reasons astronomers now believe that a significant number of core collapse supernovae leave behind black holes rather than neutron stars, even when the supernova itself looked more or less normal. The collapsar case is where the observations get truly dramatic, and where we can be most confident that a black hole has actually formed. When a gamma ray burst goes off, it's one of the brightest events in the universe. Our satellites, particularly those designed to detect gamma rays, register the burst within seconds. The signal is intense, and it has a characteristic pattern that has become familiar over decades of observations. Long-duration gamma ray bursts, which are the ones astronomers associate with collapsers, last from about 2 seconds to several minutes. During that window, an enormous amount of gamma ray energy pours through our detectors, and follow-up observations at other wavelengths quickly begin. What we typically see next, if the burst is at a distance where we can study it in detail, is an afterglow. As the relativistic jet slams into the surrounding interstellar medium, it produces radiation across the electromagnetic spectrum. X-rays, ultraviolet, visible light, infrared, radio waves, all of these appeared in sequence over hours to weeks after the burst itself, as the jet slows and cools and interacts with everything in its path. The afterglow tells us about the environment the burst went off in, about the properties of the jet, and about the surrounding gas. And for a subset of long-duration gamma-ray bursts, days to weeks after the initial event, we see something else. A supernova appears at the same location. Not a normal supernova, but an unusually energetic one, of a type known to be associated with stripped, compact progenitors. The brightness of the supernova rises, peaks, and fades over the following weeks and months, following a light curve powered largely by the radioactive decay of newly formed elements. Let me pause on that because it deserves some explanation. When a supernova explodes, the extreme conditions and the shock create a lot of radioactive nickel, specifically an isotope called nickel-56. This isotope decays into cobalt-56, which then decays into stable iron-56. Each of these decays releases energy, and that energy, deposited into the surrounding expanding envelope, is what makes the supernova bright weeks after the initial explosion. Most of the light we see from a supernova long after it went off is powered by radioactive decay, not by the initial shock itself. The initial shock only produces the very first burst of light, which is over quickly. The amount of radioactive nickel produced controls how bright the supernova gets, and how the brightness evolves over time. A normal core collapse supernova produces maybe about 1/10 of a solar mass of radioactive nickel. A hypernova can produce several times more, which is part of why hypernovae are so unusually bright. And this connects back to the failed supernova case in a striking way. If a star fails to explode and mostly just falls into a black hole, then it does not produce much radioactive nickel at all. It cannot, because you need a strong shock or ongoing energetic processes to synthesize the nickel in the first place. Without much radioactive material to power a light curve, a failed collapse produces very little light long term. That is part of why these events are so faint. There is nothing left over to keep them shining after the initial collapse. The afterglow physics of gamma-ray bursts also deserves more attention, because it is one of the most spectacular examples of how much we can learn about a distant explosion by watching it evolve across the electromagnetic spectrum over time. When a jet punches out of a dying star, it is moving at essentially the speed of light. It carries an enormous amount of energy, packed into a narrow, focused beam, and when it enters the surrounding medium, whether that is interstellar gas at typical galactic densities or a denser region of leftover material from the star's own stellar wind, It starts to sweep up that material like a plow. As material accumulates in front of the jet decelerates. It also produces a forward shock, moving outward into the surrounding gas, and a reverse shock, propagating back into the material of the jet itself. Both shocks are powerful sites of particle acceleration. Electrons in the shocked plasma are accelerated to extraordinary energies, and as they spiral in the magnetic fields threaded through the shock region, they emit radiation across the entire electromagnetic spectrum. This is the physics of what astronomers call synchrotron emission, and it is responsible for the multi-wavelength afterglows that follow gamma-ray bursts. Within hours of the burst, the visible light afterglow can be bright enough to see with a modest telescope, and it may remain observable for days or longer. As days become weeks, the peak continues to move to lower energies. Infrared observations become important. By weeks to months, most of the remaining signal is in radio waves. The whole spectrum of the afterglow sweeps from gamma rays down to radio over the course of the observation. A slow-motion demonstration of the physics of relativistic shock deceleration playing out across our sky. By carefully modeling this evolution, astronomers can extract a great deal of information. They can measure the total energy of the burst. They can constrain the density of the surrounding medium. They can determine the opening angle of the jet by looking for a characteristic break in the light curve that happens when the jet has decelerated enough for its beaming effect to weaken. They can identify signatures of dust and gas in the burst's host galaxy. And in the best cases, they can identify the redshift of the burst, telling them how far away it occurred and how long ago the collapse actually happened. So the amount of radioactive nickel is a kind of tracer for how energetic the collapse actually was. A bright, long-lived supernova had a lot of nickel and therefore a lot of energy. A dim, brief transient followed by nothing had very little nickel and therefore very little energy release, consistent with a failed or nearly failed collapse. Now, let me talk about something that dramatically shapes what we actually see, which is viewing angle, because a collapsar and any jet-driven event produces very different observational signatures depending on whether you are looking at it from within the jet cone or from outside it. Relativistic jets are extremely narrow. They typically have opening angles of only a few degrees, sometimes less. If you happen to be positioned so that the jet is pointing more or less at you, you see the full brilliance of the gamma ray burst. The light from the jet is beamed in your direction, meaning it is compressed into a narrow cone with enormous intensity. You detect the gamma rays. You see the afterglow. If a supernova is associated with the event, you may see that as well, though the supernova itself is not beamed and would be visible from all angles. But if you are looking at the same event from an angle well outside the jet cone, you do not see the gamma ray burst at all. It is not that the event was less energetic. It is that the energy was funneled into a specific direction, and you are simply not in that direction. The jet is invisible to you as a burst, even though the underlying physics was identical to a burst that another observer, positioned differently, saw as the brightest event in the sky. This has enormous implications for how we interpret observations. Most of the gamma ray bursts we detect are ones where we happen to be in the right direction to see them. For every gamma ray burst we see, there may be many more where the jet was pointed away from us and we saw nothing at all, or only some fainter, non-beamed signal like the associated supernova, or a late-time radio glow. This means that our count of gamma ray bursts represents only a small fraction of the true number of jet-launching collapsar events happening in the universe. It also means that our understanding of which collapsars produce jets is biased toward the ones we can see, which are the ones pointed at us. There may be jet-driven collapsars happening constantly, and we only catch the small fraction where we get lucky with the geometry. Now, consider what happens with different wavelengths of light, because this is another important part of the observational picture. Different processes in a collapse produce radiation at different energies, and observing across multiple wavelengths gives us different windows into what is happening. Gamma rays and hard X-rays come from the highest energy processes, particularly the innermost regions of jets and the very hot accretion disk. Soft X-rays trace slightly cooler regions and the interaction of jets with surrounding material. Ultraviolet and visible light are produced by the expanding envelope of ejected material, and by the shocks that form as that material interacts with itself and with the surrounding medium. Infrared radiation arises from dust, heated by the event and from material at somewhat lower temperatures than the visible light produces. Radio waves emerge from the interaction of relativistic particles with magnetic fields, particularly in the afterglows of jets that have slowed and expanded into the surrounding medium. By observing across all of these wavelengths, we can piece together a picture of what is happening at different depths in the event and at different times. The gamma rays tell us about the initial burst. The X-rays and ultraviolet tell us about the early afterglow. The visible light tells us about the supernova, if there is one. The infrared and radio tell us about longer-term effects, including how the ejected material is interacting with its surroundings weeks, months, and years later. This coordinated observation across bands is one of the great tools of modern astronomy. It lets us reconstruct events that no single instrument could interpret on its own. And it has been particularly useful for figuring out the connection between long-duration gamma-ray bursts, hypernovae, and the general question of when and how black holes form during massive star collapse. Now, I want to bring in gravitational waves for a moment, because they represent a completely different way of observing these events, and they may become extremely important in the years ahead. Gravitational wave detectors, like the ones that made the first direct detection of gravitational waves for emerging black holes about a decade ago, are sensitive to the ripples in space-time produced by the acceleration of massive objects. A collapsing stellar core, if the collapse is asymmetric enough, produces such ripples, and in principle, we could detect the gravitational wave signature of the collapse itself. The signal is expected to be brief and complicated. It depends on the details of how asymmetric the collapse is, how fast the material is rotating, and what instabilities develop during the collapse. For a collapse in our own galaxy, current detectors would likely see the signal clearly. For a collapse in a nearby galaxy, we might catch it. For collapses at cosmological distances, it becomes very difficult with current instruments. But if we did catch such a signal, it would tell us things we cannot learn any other way. It would tell us about the shape of the collapse. It would tell us about the rotation of the core. And in cases where a black hole forms, the gravitational wave signal would end with a characteristic ring down as the newborn black hole settles into its final state. That ring down is a direct signature of black hole formation, and it happens on the timescale of the collapse itself, not hours or days later when the shock might break out. So gravitational waves offer the possibility of catching black hole formation in real time, in a way that light-based observations cannot. This is one of the reasons why the next generation of gravitational wave detectors is so exciting. They will be more sensitive than current instruments by significant factors, and they may be able to detect collapse signals from much further out in the universe. If they do, they will give us direct observational access to the moment a black hole forms inside a star in a way that is not filtered through the opaque outer layers of the progenitor. And of course, neutrinos remain a crucial part of the observational picture. As we discussed earlier, a nearby core collapse should produce a burst of neutrinos that can be detected by underground detectors on Earth. The observation of the neutrinos from the supernova in the Large Magellanic Cloud in 1987 remains one of the great achievements of neutrino astronomy. If a collapse occurred in our own galaxy today, the neutrino detectors of the modern era would produce a much richer signal, potentially thousands of detected neutrinos rather than a few dozen, and the shape of that signal, including whether and when it cuts off, could tell us directly whether a black hole formed. Pulling all of this together now, I want to make sure the picture is clear. What we can observe in the best cases is a combination of multi-wavelength electromagnetic radiation, gravitational waves, and neutrinos. From each of these, we can extract different pieces of information about what actually happened during the collapse. And by combining them, we can build up a picture that is much richer than what any single channel would give us on its own. But I want to also emphasize the limits of what we can currently do. Most collapses happen at distances where we cannot detect neutrinos or gravitational waves. For those, we rely entirely on electromagnetic radiation, and even that reaches us in a filtered form after passing through the star and the interstellar medium and the intergalactic medium. Our inferences about the central engines of these events, about which fate the collapse actually met, are often based on indirect evidence and model-dependent interpretations. We can say some things confidently, but there are many things we still cannot pin down precisely. I also want to be careful about the way I have been discussing gamma-ray bursts and hypernovae, because the science here is subtle. Not every long-duration gamma-ray burst has a clearly identified underlying stellar collapse. Not every hypernova produces a gamma-ray burst. And the central engines of these events, while well modeled in general terms, still have important open questions in their details. The collapsor model is our best framework, and it fits a lot of the evidence, but there are astronomers who work on alternative or supplementary models, and there are individual events whose interpretation is contested. This is all healthy scientific activity, and I do not want to overstate how settled the picture is. The historical arc of how we came to connect gamma-ray bursts with massive star collapse is itself worth telling briefly, because it illustrates how observational astronomy actually progresses. Gamma-ray bursts were discovered accidentally in the late 1960s by military satellites designed to monitor compliance with a nuclear test ban treaty. The satellites detected occasional bursts of gamma rays that had no terrestrial explanation, and after some years of analysis, they were determined to be coming from space. For decades afterward, no one knew what they were. Theories proliferated. The bursts were suggested to come from nearby neutron stars, or from more distant sources, or from something else entirely. The observations were too limited to distinguish between the possibilities. The breakthrough came in 1997, when an Italian and Dutch satellite called Beppo-SX detected a gamma-ray burst and was able to pinpoint its location precisely enough for optical telescopes to follow up. For the first time, astronomers could see the afterglow of a burst in visible light and identify the galaxy it had occurred in. That galaxy was billions of light years away. Suddenly it became clear that gamma-ray bursts were not local events. They were among the most distant and most energetic phenomena in the observable universe. The connection to massive stars came a few years later. In the 1990s, careful observations of certain long-duration bursts revealed that they were accompanied by unusually bright supernovae of a type associated with stripped, compact progenitors. The first such connection was made with a burst detected in 1998, whose position was found to coincide in space and time with an unusually energetic supernova in a relatively nearby galaxy. Over the following years, more such connections accumulated, and it became clear that at least a subset of long-duration gamma-ray bursts were the deaths of massive stars. From there, the collapsar model, which had been proposed on theoretical grounds by astrophysicist Stan Woosley in 1993, became the leading framework for understanding what was actually happening at the center of these events. That sequence, from mysterious signals of unknown origin, to precisely localized sources, to identification with specific host galaxies, to connection with a particular kind of stellar death, is a beautiful example of how astronomy converts confusion into understanding. It took roughly 3 decades from the initial detection of the gamma-ray bursts to the establishment of a widely accepted physical picture for what caused them. And even now, the picture continues to be refined as we detect more bursts and study them in more detail. Similarly, when we identify a compact remnant as a black hole rather than a neutron star, we do so through indirect evidence like the object's mass, its behavior in a binary system, and the properties of any radiation it emits. We rarely get to see the black hole directly, and distinguishing a very heavy neutron star from a light black hole is still challenging in some cases, particularly given the uncertainty about the maximum neutron star mass. So what does all of this leave us with? Let me try to state the central conclusion of everything we have been exploring, because I think it is one of the most striking ideas in modern astrophysics. When a massive star dies, we naturally picture the death as an explosion. We picture a supernova. We picture bright light, hot gas, expanding shockwaves, and in many cases that picture is accurate. Many massive stars do end their lives in bright supernova explosions, but not all of them. Some of them do something much stranger. They form a black hole first, inside themselves, while the rest of the star is still there. The black hole is small. The star around it is enormous. The black hole exists in the very center, sealed off by an event horizon that is only a few kilometers across, while the entire vast body of the star continues to shine around it. And what happens next is not really a story about the star dying and leaving behind a black hole. It is a story about what the star does after the black hole has already formed. In some cases, the answer is nothing dramatic. The star just falls in. Slowly, quietly, over hours or days, the outer layers of the star sink into the newborn hole. A dim transient might briefly mark the process. Then, the star is gone, and only the black hole remains, sitting where a star used to be. In some cases, the answer is a partial escape. A weak explosion pushes some material out into space, but not all of it makes it. Fallback rains material back down onto the compact remnant, potentially transforming a young neutron star into a black hole over the course of hours. The supernova we see is real, but the neutron star at its center is not what stays. And in some cases, the answer is the most violent thing the universe can produce. The black hole forms with an accretion disk around it. Jets launch from the disk, driven by physics involving the spin of the black hole and the magnetic fields threaded through the material. The jets drill through the star at nearly the speed of light. They punch out from the stellar surface and continue into space. The visible light we eventually see from the collapse is not powered by the collapse itself. It is powered by the black hole, by the accretion, by the jets, by all the extraordinary processes that follow the formation of the horizon rather than preceding it. This inverts our usual sense of cause and effect. The visible spectacle we see in these most dramatic cases is powered by processes that begin only after the horizon closes. The sequence is inverted from what intuition suggests. Collapse comes first, the black hole appears next, and only then does the black hole decide, through its accretion and its jets, what visible fate the surrounding star will meet. That is what this whole story has been circling around. For the most massive, most extreme stellar deaths, the moment of the black hole's birth is not the final act. It is the first act. Everything after is the star deciding, based on its rotation and its mass and its structure and its history, how it wants to respond to the impossible thing that has just appeared at its center. In some cases, it falls into the void. In others, it tries to escape and mostly succeeds, but leaves a piece of itself behind. And in the most spectacular cases, it lights up the universe, powered by the very object that ate its heart. There is something almost philosophical about that image. We are used to thinking of the surface of a star as the star. But in these events, the surface of the star is the last thing to know what has happened. The star's identity is defined in these final hours, not by its outer glow, but by the singular, silent object growing at its center. And when the star finally does its most dramatic act, whether it explodes or vanishes or produces the brightest burst in the observable universe, that act is not the star's own doing. It is the black hole's doing. The star has become the stage. The black hole is the performer. That is the ending toward which everything has been building. In some of the strangest deaths the universe knows, a star does not become a black hole through its explosion. It becomes a black hole first, and then either explodes around one or falls into one, or produces something so extraordinary that we can see it from cosmological distances. The order matters. The black hole comes first, and the rest of the star, all its layers and all its light, must then decide what it wants to become in the presence of the horizon that has quietly opened inside it.